fourth video of chapter number 4, Chemical Thermodynamics. In this video, we are going to study exothermic endothermic reaction and standard enthalpy, which is a part of thermochemistry. Next enthalpy is enthalpy of atomization. Enthalpy of atomization is the enthalpy change accompanying the dissociation of 1 mole of gaseous substance into atoms. For example, Cl2. Now Cl2, when it is broken down into 1 mole of Cl and 1 mole of Cl, energy required for this reaction is 242 kJ per mole. Similarly, CH4, when it is broken down to 1 mole of carbon, 4 moles of hydrogen, the energy required for this is 1660 kJ per mole. Hence, in these reactions, the energy it is being absorbed and these reactions are endothermic. Similarly, the example for the conversion of sodium solid to sodium gaseous. The energy required for this reaction is 109 kJ. The heat absorbed when 1 mole of gaseous atoms are formed from its element. Similarly, delta H is always positive because it involves breaking of the bond. That is, whenever the breaking of a bond is there, the energy is always absorbed. Now let us see standard enthalpy of solution. Standard enthalpy change of solution is the enthalpy change when 1 mole of solute is dissolved to form an infinitely dilute solution under standard conditions. For example, NaCl plus water giving Na plus aqueous plus Cl minus, and enthalpy for the solution is plus 3.9 kJ per mole. Now this reaction is of dissolving NaCl into water. Now how exactly the reaction proceeds? Now let us see. Now in this reaction, first NaCl, when it is dissolving it in water, first it is converted into gaseous state. That is Na plus gaseous plus Cl minus gaseous. Now this is in the ionic form at this stage. Now the energy required for this is lattice enthalpy, and the energy required in this reaction is plus 776 kJ. After that, after broken down into the gaseous state, there is the hydration of the sodium and chloride ions. Now what is the hydration? That is the water molecule, it is being surrounded to the sodium and Cl minus ion. And for this, the energy required is minus 771 kJ per mole. This is called as an hydration enthalpy. Now let us see with this diagrammatic representation. Now initially in the purple and yellow balls, that is nothing but the sodium chloride ion, and this sodium chloride is being surrounded with the water initially. After some time, there is a breaking down of the sodium chloride and the sodium ions and chloride ions. Now these sodium ions and chloride ions are in the gaseous state. When they are in the gaseous state, your lattice enthalpy is involved. Here there is a breaking of a sodium chloride to Na plus ion and Cl minus, and hence there is a breaking of bond. So the lattice enthalpy is positive over here. After that, there is a hydration with the water molecule. Now when there is a hydration with the water molecule, there is a formation of a bond between the water molecule with the sodium ion and the chloride ion. Now whenever there is a formation of a bond, the energy is being released, and hence the enthalpy of hydration is negative. So with this, we can give the formula for the enthalpy of the solution, that is lattice enthalpy plus enthalpy of hydration. Hence, the enthalpy of solution is a summation of lattice enthalpy and enthalpy of hydration. In thermochemistry, we are going to study enthalpy of chemical reaction, exothermic and endothermic reactions, and standard enthalpy of reaction. Firstly, we have enthalpy of chemical reaction. The enthalpy change that accompanies a chemical reaction is the enthalpy of reaction, because the enthalpy change is the amount of heat released or absorbed in the reaction at constant temperature and pressure, and hence it is called as the heat of reaction. Consider the example AA plus BB giving CC plus DD. The enthalpy change for this reaction can be given as delta HR is equal to CHC plus DHD minus AHA plus BHB, where HA, HB, HC and HD are the enthalpies of A, B, C, D respectively, whereas small a, small b and small c and small d are the moles of the A, B, C, D. Hence, the enthalpy of the reaction can be given by summation of enthalpy of the product minus summation of enthalpy of the reactant. Thus, enthalpy of a chemical reaction is the difference between the sum of enthalpies of product and that of reactants with each substance in definite physical state and their amounts or moles being represented by coefficients in the balanced equation of the reaction. Let us now see endothermic and exothermic reaction. The enthalpy of a reaction may be positive or negative. Thus, if summation of enthalpy of the product is larger than the summation of enthalpy of a reactant, delta H is positive, which signifies that heat is absorbed. Such reactions in which heat is absorbed by the system from the surrounding are called endothermic reactions. On the other hand, summation of enthalpy of a product is smaller than the summation of enthalpy of the reactant, delta H is negative, which means that heat is released. The reactions in which heat is released from the system to the surrounding are called as exothermic reactions. For example, the first that reaction, that is N2 plus O2 giving twice NO. This is an endothermic reaction. That is, delta H in this reaction is 66.4 kilojoule. The second reaction, 2KClO3 giving 2KCl plus 3O2. This is an exothermic reaction and the energy required, that is the enthalpy in this, is minus 78 kilojoule. Now, does the enthalpy decide the spontaneity of the reaction? What exactly the spontaneity is? A spontaneous process is a process having the potential to proceed without the assistance of external energy. It means that any reaction, whenever it happens on its own without external energy, that reaction is spontaneous. A spontaneous process is an irreversible process and may only be reversed by some external energy. Is decrease in enthalpy a criteria for the spontaneity? A chemical reaction expected to be spontaneous if there is a decrease in energy, as in case of exothermic reaction. Hence, whenever the reaction is exothermic, those reactions are spontaneous. But there is an exception, that is, many endothermic reactions are also spontaneous. Therefore, it becomes obvious that while decrease in enthalpy may be a contributory factor for spontaneity, but it is not always true for all the cases. A few reactions, they are spontaneous at different temperatures. That is, any reaction, it can be spontaneous at 25 degrees Celsius but non-spontaneous at 100 degrees Celsius. Hence, in these cases, a standard enthalpy of a reaction is considered. Now, what is the standard enthalpy of a reaction? It is to compare the changes of the different reactions they have reported under standard similar set of the conditions. Now, what are standard similar set of the conditions? Now, these are nothing but the thermodynamic standard state. That is, whenever the reaction is occurring at pressure of 1 bar and 298 Kelvin temperature, that reaction can be considered as standard enthalpy of the reaction. If the reaction involves species in the solution, its standard state refers to the 1 molar concentration. Now, for example, in these table, that is, the substances are given and in the standard state they are observed in which state are given. That is, the hydrogen in the standard state is in gaseous form, oxygen is gaseous, chlorine is gaseous, bromine is liquid, carbon is solid, which is a graphite, water is liquid, carbon dioxide is gaseous, CH4 is gas, and sodium chloride is solid, which is a crystalline form. Hence, standard enthalpy of reaction is the change accompanying the reaction when reactants and the products involved are in their standard states. Now, what is a thermochemical equation? A thermochemical equation is a balanced chemical equation that includes the physical state of all reactants and product. That is, the energy changes are also included in it. Now consider these two examples. Now in both the examples, the atoms are in their physical states and these are the balanced equations. Hence, they are called as balanced thermochemical equations. Let us now see standard enthalpies. Firstly, we have standard enthalpy of combustion, which is denoted by delta Hc naught. So whenever the word standard comes, we denote by the symbol H naught. The standard enthalpy of combustion is defined as the enthalpy change accompanying a reaction in which 1 mole of a substance in its standard state is completely oxidized. Consider the reaction oxidation of ethene. Now ethene, when it is oxidized to CO2 and H2O. In the above reaction, the standard enthalpy change of oxidation reaction minus 13 kJ is a standard enthalpy of combustion of ethene. Now let us consider another enthalpy, that is the standard enthalpy of formation, which is denoted by the symbol delta HF naught. The standard enthalpy change of formation of a compound is enthalpy change that accompanies a reaction in which 1 mole of pure compound in its standard state is formed from its element in their standard state. Consider the reaction for the formation of methane, that is C plus 2H2 giving CH4. Now enthalpy for this reaction is minus 74.8 kJ. Hence, the enthalpy of the reaction can be given by summation of enthalpy of formation of the product minus summation of enthalpy of the formation of reactants. Let us see now very important concept, that is bond enthalpy. Now what is a bond enthalpy? The enthalpy change required to break a particular bond in 1 mole of gaseous molecule to produce gaseous atoms or radicals is called bond enthalpy. Now whenever the bond is broken and the products are formed, it means that the reactants bond are broken and the products bond are formed. Hence, we can give the bond enthalpy as summation of enthalpy of the broken bonds, that is the reactant, minus summation of the enthalpy of bond formed, that is products. Thank you all for watching the video. Hope you must have understood everything.